Okay, now we're going to skip a lot of stuff here. We're going to do some trig ones. 41. So we have y is equal to the cosine of 3x. So we're going to let u, I put parentheses in there. It's not shown, but this emphasizes this is the argument of the cosine. So with that known, we would let u equal that, and we would let f of u equal the cosine of u. The derivative of the cosine is negative the sine. The derivative of 3x is 3. So f prime of x is equal to f prime of u times u prime of x. F prime of u is negative the sine of u times u prime of x, which is 3. So we get negative 3 times the sine of u, but u is 3x. So f prime of x is negative 3 sine of 3x. 44. So we have h of x is the secant of x squared. So this does not equal the secant of x quantity squared. It's really the secant of the quantity x squared. So that's the one we're doing. So our u of x is going to be x squared. H of u is the secant of u. Plug that in there, you get that. H prime of u, what is the derivative of the secant? Look in the book. Secant of u, tangent of u. The derivative of x squared is just 2x. 2x. H prime of x equals h prime of u times u prime of x. So we get the secant of u times the tangent of u times 2x. Bring the 2 out front, then the x. Then we have the secant of u, but u is x squared, and the tangent is tangent of u turns into tangent of x squared. And we want to put those parentheses there, even though they weren't originally there. It's good to keep that. .49. So we have f of x is equal to the cotangent of x divided by the sine of x. So do we really need to use the chain rule? Because it's not really a chain. It's not something as a function of something else. It's just a quotient. So one way, there's a couple ways of doing this one. You could just use the quotient rule. This would be f of x. This would be g of x. But a lot of times you want to see if there's something by changing everything to sines and cosines. So if I change cotangent to cosine over sine, I get that. And this is the same as the sine over 1, so if you take the reciprocal of that and multiply it, you'd end up with the cosine of x divided by the sine of x quantity squared. So, is that any easier? I don't know. Because that's cosecant, so it's cosine times cosecant, then you could use the product rule. Yeah, let's do that. So, there are a lot of ways you could do this problem. Cosine of x times cosecant of x quantity squared. So we're going to actually use a kind of combination of the chain rule and the product rule, because this is one product, this is the other part of the product, but this one we have to evaluate using the chain rule. So let's do that separately. So let's say ddx of the cosecant of x quantity squared. Let's call, so that's h of x. So let's say h of x equals cosecant of x quantity squared. So we'd use the chain rule on this, and we'd say h of u is u squared and u of x is equal to the cosecant of x. Take the derivatives, so h prime of u is 2u, u prime of x is equal to, well, the derivative of the cosecant is negative the cosecant times the cotangent. So h prime of x is 2u times negative cosecant of x cotangent of x. And if you plug in u is cosecant. So you get 2 cosecant of x times 1 minus cosecant of x cotangent of x. And then simplifying it, bring the negative sign out in front with the 2. Combine the two cosecants together, cosecant of x squared times the cotangent of x. So that would be h prime of x. Now we go over here and use the product rule. So let's say this is, we'll call this g of x, and we'll call this h of x. So that's g of x times h of x. So from the quotient rule, we know that f prime of x is. So it's basically g prime of x times h of x minus g of x times h prime of x, all divided by, oh, this is product. I don't have to use the quotient rule. What am I doing? Crazy. Okay. So in this case, it's going to be g of x times h prime of x plus g prime of x times h of x. So we're going to call, so g of x is cosine. So you have the cosine of x times h prime of x, which is negative 2 cosecant of x squared times the cotangent of x. So that's the first part. This times the derivative of that. And then we have plus g prime of x, which is the derivative of this is minus the sign. So you get negative the sine of x times h of x, which is cosecant squared. Cosecant of x quantity squared. Okay. That's right. Okay, let's do a little simplification here. So we've got negative 2. If we change the cotangent to the cosine of x over the sine of x, so that also is equal to the same as the cosine of x times the cosecant of x. 1 over the sine is the cosecant. So we get negative 2, and then we'll have cosine squared of x, and then we'll have cosecant times cosecant squared, so we'll get cosecant of x cubed. And then the second part is we get the sine of x times the cosecant of x squared. So I'm just going to stop here for a second, just to make sure I'm not getting completely off course. So it takes a lot of bits to do this. Okay, well, believe it or not, I'm actually on the right track here. I didn't make any mistakes. That's the problem with trig things. You never know exactly how you're going to end up. Okay, let's do this. You'll get -2 cosine squared of x divided by the sine cubed of x. So cosecant is 1 over sine, so you get that. Now the second term, you'll get the sine of x divided by the sine of x squared, because cosecant is 1 over the sine, so that's that. Now I'm going to try to find a common denominator here, which is sine cubed. So if I multiply the second term here, so that's sine cubed, if I multiply the numerator and the denominator by sine, I'll get sine squared of x over sine cubed of x. And this is the next to last step, so we can combine the common denominator. So what you get is negative the sine squared of x minus 2 cosine squared of x divided by sine cubed of x. Then you can substitute in for the sine of, so sine squared x plus cosine squared x equals 1. So negative sine squared of x is equal to, so bringing that over, it becomes negative, and I bring that back over here, so you end up with cosine squared x minus 1. Okay, this goes to the other side, becomes negative. This comes to the right left-hand side, becomes negative. So you have cosine squared x minus 1 is equal to negative sine squared of x. So we can make that substitution here for there, and so you get cosine squared of x minus 1 minus 2 cosine squared of x, all divided by the sine of cubed of x. And so 1 cosine squared of x minus 2 cosine squared of x is going to be negative 1 cosine squared of x, all over sine cubed of x. And that's the answer that they put in that's in the book. Now, there's a whole slew of different ways you could do that. What they actually did in the book was they used the quotient rule. So they went to this point. From this point, they used the quotient rule. I changed it into a product and then used the product rule, but it comes out the same. If you're interested, let's just do it. If you're not interested, you can turn it off. So I don't know if anybody will watch me now, but here, let's go ahead and paste that. I'll show you how it comes out to be the same answer. And so that's the quotient. So let's call f of x equal to the cosine of x. We'll say g of x is equal to the sine of x quantity squared. So f prime of x is negative the sine of x, and g prime of x. So I'm going to do this in my head. I'm going to explain what I'm doing. So I'm going to do the chain rule in my head. So there, I'm going to talk through it. So you treat this as the quantity. You got basically got u squared. So when you take the derivative of u squared, you get 2 times u. So that's the first part, 2 times u. And then you multiply by the derivative of what's in the parentheses. And the derivative of the sine is the cosine. So you could do this on a separate page, but that's what you get. Okay, so then use the quotient rule. So let's call this h of x. So h prime of x is f prime of x times g of x minus f of x times g prime of x, all divided by g of x quantity squared. So f prime of x is negative the sine of x. G of x is sine of x squared. We subtract f of x, which is the cosine of x. And we multiply by g prime of x, which is 2 sine of x cosine of x. And we divide by g of x squared. So we get the sine of x quantity squared, the whole thing squared. Okay, so what you'll see is there's a sine of x here and there's a sine of x there, and there are 4 sine of x's in the bottom. So if we cancel out one sine of x, we get negative sine of x squared minus 2 cosine of x squared, all divided by the sine of x cubed. We just figured that out, that is equal to, what do? We just had it a second ago, so let's just go copy it. Yeah, so I come down here, so we'll copy that, hopefully. Okay, Control C, go to the end, Control V, Control V, I don't know why I didn't do that. Let's go back again. Let's do copy. Copy. Paste. There it is. Okay, so there's our substitution. So let's go over here. So this is equal to that. So you get the cosine squared of x minus 1 minus 2 cosine squared of x, all divided by the sine cubed of x. And again, that simplifies down to negative 1 minus cosine squared of x, all divided by the sine cubed of x, which is exactly the same answer. Okay, so let's see here, 51. So we're going to jump back to the ones involving trig functions for a while. 4, y is equal to 4 secant squared of x. So we rewrite that as 4 secant of x squared. And we'll call this f of x. So f of x, f prime of x, well, yeah, no, f of u, so we need to do f of u and u. So u is secant of x, and f of u is equal to 4x, the 4u squared. Okay, f prime of u is equal to 8u. U prime of x, sorry I didn't put u of x there. Secant derivative, secant, looking on page 136, is the secant of x tangent of x. So f prime of x is f prime of u times u prime of x. And then the final answer is 8 times u, which is secant of x times secant of x tangent of x. And so we can combine those and you get 8 secant squared of x tangent of x. And that was problem 51. Let's see what the book says. 8 secant squared of x tangent of x. Good shape. '54. So 54 says h of t is 2 cotangent squared of pi t plus 2. And so this is actually one of those, this may not be obvious to you, but this is where I actually have to do 3 levels. Because if we write this as h of t is 2, so it's the cotangent of pi t plus 2 quantity squared. So you see we have actually two sets of parentheses. That kind of teases into the fact that it's a 3 levels. So what you actually have to do is you have to do something like h of v is 2v squared. Okay, so this whole bit in here is v. Then you say u of, let's see, how do I want to do this? So what you'd say is v of u. So what we have there is you go to the next level in. So the outside level is a squared thing. Then you'd say the cotangent of u. That would be your second level. And the final level would be the inside parentheses. So you'd say u of x is equal to pi t plus 2. So then you take the derivative, and if you see, if I plug that into here, I get the cotangent of this term, and then if I plug that into there, I get 2 times this whole thing squared. So it all makes sense. Believe me. Okay, the derivative there is 4v. I'm taking the derivative with respect to v. Here, v prime of u, I'm taking the derivative of this with respect to u, and the derivative of the cotangent is minus the cosecant. I'm going to write it correctly first. Cosecant squared of u. And then u prime of x is just, or pi, I guess it's t, sorry. Let's put t in there. U of t. U prime of t, the second term is a constant, so that goes to 0. And the derivative of the first term is pi. Because the derivative of t is 1, 1 times pi is pi. Okay, now the way you work this is you multiply all these things to get 3 things together. So you'd say h prime of t is h prime of v times v prime of u times u prime of t. So you kind of plug that into there, and then you plug that into there. Okay, so, and it's kind of a multi-step thing. So since I'm going to ask you to do this on a test, I'm going to do it, and hopefully some of you guys will understand what I'm doing. So it's 4v. V is the cotangent of u, but u is pi t plus 2. So that's this first part, 4v. V is cotangent of u, u is pi t. Okay, so that's the first part. Then you have v prime of t, which is negative the cosecant squared of u, but u is pi t plus 2. So that's the second term, negative cosecant squared of u, plug in u, and then you multiply by u prime of t, which is pi. So we clean this up a little bit, and we have a negative sign, we have pi, and we have 4. So it's negative 4 pi, and then we just write the rest of the stuff out. Cotangent of pi t plus 2 times the cosecant squared of pi t plus 2. And we check the answer in the book. Minus 4 pi, cotangent of pi t plus 2 plus cosecant squared of pi t plus 2. Exactly. So, let me just go back and explain it to you again here. We have to break it into 3 because we have 2 parentheses. We have this parenthesis and this parenthesis, so there's an extra parenthesis involved. So I say it's 2 times this quantity squared. We call this quantity v. So v is this quantity, cotangent of this. But so I write cotangent, but rather than the cotangent of this argument, I use the cotangent of u. So this is u of t, is the final thing in the parentheses. 2 cotangent of this whole thing squared. Then you take the derivatives. 2 times 2 is 4, b to the 1 power. The derivative of this with respect to u, you look it up in the table, you get that. Here we just use the derivative of t is 1. So we have pi times 1. Then you multiply all these derivatives together, so you get 3 parts of the chain rule. The first part is 4 times v. V is cotangent of u is this. So you get 4 cotangent of that whole thing. Then you multiply by the second term, negative the cosecant squared, negative cosecant squared of u, but u is pi t plus 2. And then finally multiply by u prime, which is pi. We take all the constant terms and move them out front, and then we have the other two parts. Okay, 57. If you just watch 54, this is actually easier. Y is equal to the square root of x. Everybody gets so bogged down in these things that they think, oh, this next one must be even harder. Actually, the second part is also a three-parter. And we're going to just do these two parts separately. So we know what the derivative of that is going to be. It's going to, so if I said y prime, the first one is going to be 1 over 2 the square root of x. Okay, we've done that 20 times already. Now you have the second part. So you got 1/4 times the derivative of this thing. So let's add the page, and then we'll just do it. So let's say, we'll say f of x is equal to the sine of quantity 2x quantity squared. So really another way of writing this is the sine of big parenthesis 2x squared close parenthesis. So there are two sets of parentheses. We're assuming because the square is not here, it's not the sine of 2x quantity squared, it's the sine of the quantity 2x. This whole thing is in part of the sine. So just like before, we do f of u, and the outside parentheses go with the sine, so we have the sine of u. And then we have, pardon me, f of v. Let me introduce an extra variable. Sine of v, f of v is the sine of v. Okay, now we need to know what v is. Well, v is this part right here. So it's equal to u squared, because u of x is 2x. So if we plug 2x into there, we get quantity 2x squared, and then we plug that into there, and you get the sine of this whole thing. So that makes sense. And now we take the derivatives, which are the easy part. So you get cosine of v prime of x, v prime of u, sorry, is 2u, and u prime of x is just 2. U prime of x equals 2. So to find the f prime of x, you take the cosine of v times v prime of u, which is 2u, times u prime of x, which is 2. So the cosine of v, what do we do? Cosine of v, which is u squared, times, and then you plug that in there. So what you get is the cosine of the quantity. Okay, 2. So we have u cosine of v times u squared. U is 2x. We square that, and we cos. So it's just like the original function, except it changes to cosine. Then you multiply by 2u, but u is 2x. So that's what that's 2 times u. 2u is v prime of u, but you plug into u to keep it all in terms of x. And then finally you multiply by u prime of x, which is 2. So now let's get everything straight here. 2 times 2 times 2 is 8. So we have 8, we have an x, and then we have the cosine of the quantity 2x squared, quantity closed. So that's f prime of x. Call that. So now all we have to do is come over here and just plug it in. So we get 1/4 times 8x times the cosine of, I'm just going to use their terminology, so I'm going to take one of those parentheses off so it's consistent with the original expression. And then we go one last step. We don't do anything with the two terms because it's got cosine and Just right, didn't do much. 8 divided by 4 is 2, so you get 2x cosine. I'm going to put it back in there. I just don't like leaving that out. So it's all clear as mud. 57, let me just check. 1 over 2 square root of x plus 2x cosine of 2x quantity squared. So that's right. Okay, now we're going on to 62. Really nothing new exciting, it's just a different question. So we have to use what we've learned to calculate the derivative, and then we just plug x or t into whatever problem variable is. So in this case we have 1 over the quantity x squared minus 3x squared. If you plug x equals 4 in here, the answer you get out is 1/16. I'll show that. So you get 1 over 4 squared, which is 16, minus 3 times 4. Then you square that. 16 minus 12 is 4. 4 squared is 16, so you get 16. So that's what the coordinate pairs, that's the xy coordinates of this function at x equals 4. But what they're asking for is what is the derivative? And what we've done so far is we've derived the expression for the derivative, but we haven't actually given you a number because we haven't plugged in an x value. So that's all we have to do. So that's the question. What is f prime of x? So what we're going to do is we are going to break this up into 2 parts. So we have f of u is equal to 1 over u squared, and u of x is equal to x squared minus 3x. Plug that in there, you get that. So the chain rule, it's kind of like everything. We write the functions and then we take the derivatives of the functions. Okay, this is equal to x to the minus 2. So the derivative is negative 2 u to the minus 3, which then becomes negative 2 over u cubed. And then we do u of x. So u prime of x is 2x minus 3. 2x minus 3. Okay, so now the chain rule says we multiply these things together to get f prime of x. So we get negative 2 over u cubed times 2x minus 3. So it's this times that. And then we substitute in for u, so we'll get negative. Let's go ahead and just multiply this out. So you get 4x, negative the quantity, 4x minus 6 divided by u cubed. U is x squared minus 3x. X squared minus 3x. And we cube that. So that's f prime of x. So just have to plug in for, we want f prime of 4. F prime of 4. So we get negative the quantity 4 times 4 minus 6, all divided by 4 squared minus 3 times 4 cubed. So I'll just put x in here for all those. And we get negative, and that's 16 minus 6 is 10. In the denominator we get 16 minus 12, which is 4. 4 cubed is 64. So if I haven't made a mistake, the answer should be 10/64, or negative 10/64, which actually can be simplified to negative 5/32. So that's your answer. We just took the derivative using the chain rule. Once we had the derivative in terms of x, we just plugged x into the equation and came up with a number. Okay, we're number 68. So this is the second kind of problem we've had where you calculate the equation to the tangent line. So we've done this before. We just have to find the derivative, plug in the x value to find the value of the derivative, which is the slope of the tangent line, and then you use the point slope form of the linear equation to come up with the line. So step number one, let's take the derivative. And we're going to have to use the chain rule and the product rule here. So let's just change this to h of x so we can. So I'm going to say f of x is equal to 1/3 x, and g of x is equal to the square root of x squared plus 5. Now, the second one we have to use the chain rule for, so let's add a page and do that. So we'll let g of u equal the square root of u, and u of x equal x squared plus 5. Plug that in there, we get that. We take the derivative of each expression. So g prime of u, 1 over 2 the square root of u. U prime of x, 2x. Therefore, g prime of x is equal to g prime of u times u prime of x. Then we plug in u, these cancel out, and so we end up with x in the numerator and the square root of u in the denominator. So that's g prime of x. So we can go over here and write that in. X over the square root of x squared plus 5, and f prime of x is equal to 1/3. Okay, the product rule says we just cross multiply and add them together. So we can say h prime of x is 1/3 x times this, so we'll get x squared in the numerator. In the denominator we get x squared plus 5. The second term is this, 1/3 times the square root of x squared plus 5. So now we got a page, and we just plug in 2. So we'll get 2 squared over 3 times the square root of 2 squared plus 5 plus the square root of 2 squared plus 5 all divided by 3. So we have 4 divided by 3. 2 squared is 4. 4 plus 5 is 9. Square root of 9 is 3. So this term here is also 3. So that's 4/9 plus 3/3 or 9/9. So that gives us 13/9 as the value of the derivative, which is this is the slope of the tangent line. Okay, so now what do we do? Well, what was the x? What was the y value? 2, 2, 2. Okay, let me add a page here. So x1 equals 2, y1 equals 2, m is equal to 13/9. So we have our point slope form of the linear equation. Y minus 2 is equal to 13/9 times x minus 2. Let's just stick 2 in for x and y. And then we can, let's see, -2. We have 13/9 x minus 26/9. 2 times 13 is 26. If we add 2 to both sides, we'll get y is equal to 13/9 x minus 26/9 plus 18/9. So when you add 2, that saves 18/9. You get y is 13/9 x, and 26 minus negative 26 plus 18, that's 8. So that's going to be -8/9. Okay, let's check to see if that's the right answer or not. So that was problem number 68. 13/9 minus 2. Yep, that's it. So that's the equation for the tangent line. They don't ask you, do they say, use a graphing utility to show it? Okay. So we're going to do that. So let me write this down on a piece of paper so I don't have to go back. So the function itself is f of x equals 1/3 x square root of x squared plus 5. The equation for the line is y equals 13/9 x minus 8/9. Okay, so now we're going to have to go open up the graphing program. So I have that open right now. Okay, stop sharing my smartboard, start sharing my graphing program. So 1/3 times x times square root of x squared plus 5. Let's just graph that and see what it looks like. And just kind of eyeball what we think is going to happen. And we're looking for x equals 2, which is right there. Let's zoom out just a little bit, see what this function looks like. 60, oh, that's 68. Yep, okay, I was looking wrong. Drawing, I thought I didn't know what it looked like. Okay, so it looks like, 2, you'd have a positive slope. It's going to look something like that. If I ballpark it down, I'm going to be negative something between, around -1, which we have a -8/9, which is really close to 1. So it looks like it's going to work out. So now we put the equation for the line in, which is going to be 13 divided by 9 times x minus 8 divided by 9. And I always think it's great when this works. So there you go. So you can see that the blue line is the tangent line at x equals 2. You can see that, if we keep zooming in, at x equals 2, that the blue line is always on this side. The only place it touches is exactly at x equals 2. So that's pretty cool. Okay, so this is problem 83, section 4. So it's asking us to take the second derivative of a function. So the second derivative is just the derivative of the first derivative. So we write our function out. And we can use the chain rule to take the first derivative. So the chain rule says, so we don't have to apply the chain rule to the 2, so we just bring that down. So what we do is we treat this is the u of x. So we take the derivative of the u part. So we have u cubed. So the derivative of u cubed is 3u squared times the derivative of what's inside the parenthesis, which is 2x. So this is f of u is u cubed. Derivative of u cubed is 3u squared. U of x is x squared minus 1. U prime of x is 2x. So then you can stick u back in. So you get 6 times x squared minus 1 squared. Actually, let's multiply all these things out. 2 from here, the 3 from the exponent, 2 from the derivative. So that's 12. 12, and let's move the variable by itself out front, and then we'll put the thing in the parentheses. So that's the proper arrangement. Now we could, because this is like a square, we could use FOIL to multiply that out, and we could get 3 separate terms, or we could use the chain rule. Let's do it both ways. We use the chain rule. Well, you have to use the chain rule in conjunction with the product rule. So here we have this times this whole thing. So this is the chain rule, but product rule, but you got to use the chain rule. So trying to decide what to call this thing. So if we want to take the derivative with respect to x of the original derivative, so that's going to be the second derivative, you're going to have the constant 12, and then you're going to have this derivative of the product. So you take the first term, which is x, times the derivative of the second part. Well, using the same chain rule thing, you're going to bring the exponent down. You're going to leave the argument in the parentheses the same. You're going to reduce the exponent by 1. And then you're going to multiply it by the derivative of the term in the parentheses. So it looks very similar to what we did up here. Here we have 3u squared times 2x. Here we have 2 times u times 2x. So the first term times the derivative of the second term. The second term is using the chain rule. And then we have the derivative of the first term. Well, the first term in the product is, I think I'm getting ahead of myself here. I am. Sorry. I'm doing 2 things at one time. You got to be careful about that so that you guys do that too. So let's do it again. So what we're going to do is we take the first term times the derivative with respect to x of the second term plus the derivative of the second term, or the second term times the derivative with respect to x of the first term. So that's just me writing out the product rule. First term, derivative of the second, plus the second term times the derivative of the first. Okay, so now what we're going to do is we're going to just do what I did a second ago, but so we have x times the derivative of this thing. So that's 2 times 2 from the exponent. Keep the argument the same here in the parentheses. Reduce the exponent by 1. Multiplied by the derivative of what's inside. So that's this first term completely done here. The derivative of x with respect to x is just 1. So the first term stays the same because we don't need to take a derivative of that times 1. Okay, so now we just need to simplify. One thing we could do is first just rearrange these terms. So you multiply the 2 constants together, you get 4. And the x's multiplied together give me x squared, and that's multiplied by x squared minus 1. So this is the first power, so it's just x squared minus 1. 2 times 2 is 4, x times x is x squared, x minus 1. The second term, we can drop the 1, so we get x squared minus 1 squared. So let's just multiply everything out. 4x squared times x squared is 4x to the 4th. 4x squared times negative 1 is negative 4x squared. When you use FOIL on this, the first terms together are going to give you x to the 4th. The inner terms are going to give you negative 2x squared, and the final term is going to be 1. Negative 1 times negative 1 is positive 1. And now we can combine like terms. So we have x to the 4th, we have 5 of those. We have negative 6x squared, and we have plus 1, and that's probably good. So that is what we would call f double prime of x. Now the other option would be that I could have gone at this point. I could have multiplied this out. So starting with the first derivative, I'm going to get 12x times, okay, so I just did this a second ago. Where was it? Here. So I got x to the 4th minus 2x squared plus 1. Okay, now take the derivatives. of each one of those. Well, actually, we need to multiply this thing out first. So we've got all the x terms. So we still haven't taken the derivative. I'm going to factor the 12 out because we have 12 factored out here. So you get x to the 5th minus 2x cubed. This is multiplying each term by x. So these multiplied by x give us that. Okay, so now we can take the derivative. So f double prime of x is 12 times the derivative of x to the 5th, which is 5x to the 4th, times minus 2 times x cubed. Take the derivative of that would be 3x squared. 3 times 2 is 6, so you get negative 6x squared. Derivative of x is 1. And you see we get the same answer. So I guess that's it. Okay, so this is 103. So let's read the problem, page 139. 15 centimeter pendulum moves according to the equation theta equals 0.2 cosine of 8t, where theta is the angle, the displacement for the vertical in radians. T is time in seconds. Determine the maximum angular displacement and the rate of change of theta when t equals 3 seconds. So here's the equation. The angular displacement as a function of time is 0.2 cosine of 8t. And it says, what is the maximum angular displacement? Well, we don't even have to use calculus for that, because the cosine maximum value is either positive 1 or negative 1. So theta max is equal to 0.2 radians. How many degrees is 0.2 radians? This is just a side question. So you take 180 divided by pi. Okay, I'm going to find my calculator. This is physics, something I'm going to tell you about physics. Okay, so 0.2 times 180 divided by pi, 11 degrees. 0.5 degrees. Turns out pendulums are only sinusoidal or cosinusoidal in this case when the angles are small. So 11 degrees is pretty small. That's usually where the sine of the angle is equal to the angle in radians. So we've got if you take the sine of 0.2 radians, we get sine of 0.2. You get, oh, got to put in the right units here, right mode. Okay, so the sine of 0.2 is 0.198. So 0.2 is approximately equal to 0.198. It's within 1%. Is that right? It's less than 1%. 0.002 divided by 0.2 times 100. It's 1%. It's within 1%. So with that kind of angular displacement, this equation actually is pretty good. Now, the second question is, what is the rate of change of theta when t equals 3 seconds? So the rate of change of theta, and since it's a function of t, we don't have to use implicit differentiation because the variable we're taking the derivative with respect to is the same variable that the equation is defined in. So we just have to use the chain rule. If you remember, what we did to find the derivative is we took the derivative of the cosine, which was a sine. We kept the argument the same, and then we multiplied by the derivative of the argument, which is 8. Derivative of t is 1, so you get 8 times 1. So the answer, 8 times 0.2 is 1.6 sine of 8t. And think back visually when you see this. Try to remember, what happens when you have a constant times time as the argument for a trig function. Well, this is one, this would be one oscillation in 2 pi radians. But if you have 8, you get 8 oscillations, and therefore the slope of the line is going to be much higher. It's going to be 8 times higher than if it was going from 0 to 2 pi. So don't forget to do that. Okay, now, so that's the rate of change. So all we have to do for the second part is easy. We just plug t equals 3. So at t equals 3 seconds, the rate of change in the angle with respect to time is equal to, so that's at 3 seconds, is 1.6 times the sine of 3 times, well, 8 times 3. And you just plug it in your calculator. Just make sure it's in radians. So you get 1.6 times the sine of 24. And I get negative 1.45 radians per second. That's the rate of change in theta with respect to time. And I'm just going to double check, make sure that's the right answer. I don't think I can make anything wrong. That's a pretty easy problem. So, but I don't want you to make a mistake and then you're like, I don't understand. So the rate of change is 1.45. And does it say determine the maximum angular space in the rate of change? Okay. Because it's interesting, in the book they say negative and then they, oh, I know. Okay, so that's why so actually I did have one error here. The derivative of the cosine is negative sine, so that should have been negative. That should have been negative. So that becomes positive. So it's actually positive 1.45 radians per second. Got a little sloppy there with my derivative. I was so busy thinking about explaining using the chain rule that I forgot to do the right thing there. Okay, so the last problem is 104, and similar to 103, it's a oscillating situation. What you have is waves, ocean waves. If you remember in class, we talked about a spring and a mass. We said that if you plotted the vertical displacement as a function of time, you'd get a sinusoidal thing. And this is this is not a wave, but it's kind of like waves behave. You have a mass, and you have some form of storing energy. You have inertia and some form of storing energy. For a wave, you have the same kind of thing. This energy storage is the potential, the energy associated with this being higher than this part. So that's the energy part. That's actually the, pardon me, that's the gravity's the spring part, and just the mass of the wave, the water mass, is the mass part of it. And because of that, it behaves such that you can represent the displacement of the wave at a particular point in space. It'll go up and down like that around some equilibrium position. So it's A times the cosine of omega t. It says the boy moves a total of 3.5 vertically. So that 3.5 is the total distance traveled. So the actual amplitude, A, is the distance from the middle part to the maximum, and also the distance from the middle point to the minimum. What they've given is they've said that the total variation is 3.5 feet. So for that, in that case, A is 3.5 divided by 2, which is 1.75 feet. And that's because this equation is such that the cosine minimum is -1, so it goes down 1.75 feet from the median point, and it goes up 1.75 feet, and it gives you a total up and down of 3.5 feet. And it says it returns to its high point every 10 seconds. So what that means is the period of oscillation is 10, well actually, yeah, the period is 10 seconds. So if you think about a standard sine or cosine wave, it goes up and it goes down, and the period is 2 pi. So that's 6. This is 10. So this omega has to be such that it works out correctly. So typically, if omega equals 1, then you get this result. So we need omega to be actually, because the actual oscillation takes 10 seconds instead of 6 seconds, it's going to be a little bit longer. It's going to be like this, and then it'll come back and at 10. 2 pi is 6.2 something. So to make the thing stretched, compared to the last problem, which it was shrunk, this number here is actually going to have to be less than 1. So how much more less than 1 is? Well, it's just the ratio of these two things. So it was going to be 2 pi divided by 10. If it was 10 over 2 pi, then you'd have a number greater than 1, and that would cause things to happen more quickly. But we want things slower. So that, just from kind of reasoning about what's going on here, omega is going to be 2 pi over 10. If the period was 2 pi, you'd have 2 pi over 2 pi, and you get a coefficient of 1, which would revert back to what we normally have for a normal sine wave. So now we can write the equation. The displacement is, as a function of time, is 1.75 times the cosine of 2 pi divided by 10 times t. There are formulas that say the frequency of the oscillation is 1 over the period. So this is, period is cycles, seconds per cycle. Frequency is cycles per second. We also know that 2 pi f is equal to omega. Well, I know that. You don't know that yet, but in physics we'll figure that out. So if I solve for what I'm looking for here is omega, and f is 1 over t. So if I plug f in as 1 over t, I get 2 pi over t is equal to omega, and t is 10 seconds. So I get 2 pi over 10. So that gives me the same result. So once we have the equation, to answer the questions, it's just a matter of dealing with the equation. Well, actually, it says write an equation describing the motion of the boy if it is at its high point at t equals 0. Well, what is that? What is the t equal high point at t equals 0? Well, we choose the trig function such that it reaches a maximum value of 1. Trig function has to equal 1.0 at t equals 0. Well, that turns out to be the cosine function. If you plot cosine, it looks like this. If you did the sine, it looks like that. So if you wanted the displacement or the oscillation to be 0, halfway between, you'd use the sine, but in this case we're using the cosine, which is what they already told us to do anyway, so there's really nothing new there. So the answer to to answer the first part of the problem. It says, and then it says determine the velocity of the boy as a function of time. So this is a displacement. The velocity is going to be dy dt, the rate of change in the y coordinate of the wave. So we just have to take the derivative. So we get 1.75. Then just use the chain rule. So the derivative of the sine, cosine, is negative the sine. I keep the argument the same. And the chain rule says we have to multiply by the derivative of what's in there. Well, the derivative of what's in there is just the coefficient, 2 pi over 10. So then we can just clean it up a little bit. And so we'll get negative 1.75 sine of, now let's move the constants out front. So it'd be times 2 pi over 10 times the sine of 2 pi over 10 t. And if 2 times 1.75 is 3.5. 3.5 divided by 10 is 0.35. So we get negative 0.35 pi sine of 2 pi over 10 times t. And that should be the answer. Let's check the book. Okay. Yeah. So I probably would have expected you. I did something I've marked off for you guys before. 2 over 10 is 5, 1/5. So we could simplify that down to pi t over 5. Otherwise, everything's good.